1 o'clock. So this is, we are jumping to chapter 16, because in between you have heat and thermodynamics, so on. We will skip them all and we'll go to electricity. So probably it will be more relevant or more application, because your cells are electric, right? You know that. So electricity is important even in medicine, in life sciences. It's going to be a short one. I'll be skipping topic 2. We'll introduce electricity is coming from electric charges. Because we have charges, the positive charge and negative charge, that's where the electricity is coming from. Because with the associated with the charges will be forces between charges, that is electric force. Then we have the electricity being driven, and you have the current, electric signals in the nerves, and so on. Number 3, we will look specifically at life sciences applications. Number 4, we will introduce this concept of electric field on top of the electric force as another concept, electric field. Like gravitational force, we have the gravitational field. Like electric force, we have the electric field. Right. This molecule, water molecule, so we've seen this before. It is 1 oxygen and 2 hydrogen. The whole life depends on water molecule. So water molecule being a polar molecule, meaning one end of the molecule is positive, the oxygen end, and the hydrogen end is positive. So there's a separation of charges. So we call it polar molecule. So water being a polar molecule is the reason why water is so much very significant in the life process and so on. Water molecules are the dipole structure. So we will talk about the dipole, mean it is polarized, right? Because this is positive side and the negative side, so it's a dipolar structure. That's why I call it polar molecule. So you know why that happened? Because oxygen is hungry for electrons, so it will try to, although they're supposed to share equally. Please put your screen down, pay attention to this lecture, please. Down, yeah. So one end is a negative, other end is positive. Hydrogen side will be losing the electron to a little bit. I mean, that's a very slight polarization. So this side will be slightly negative, this end will be slightly positive. That has a lot of significance. Right, now we come to the force. We introduced this before about the electric force. When you have 2 charges, let's say the charge magnitude, one of them is Q1 and Q2. Let me draw the 2 charges. The charge can be how much charge it has is called the Q, and the SI unit is Coulomb. Because it's the Coulomb, Charles Coulomb, he's the one who discovered this formula for the electric force. If you have 2 charges, they will exert force on each other, and the electric force is given by this formula. This is a constant. It's also written as K, or 1/4πε0, in 2 different ways. It is proportional to the product of the charges divided by inversely proportional to the distance square. So it's an inverse square law, like the gravitational force. It almost looks similar. The form almost looks similar. There it is the masses, product of the 2 masses. Here the product of the 2 charges. So with this constant epsilon0 is called the permittivity of free space, and it has this value, very small value. Well, but I know this K is a big value, because 1 over that, right? The value of K is actually a big value. The proportionality constant K is 10⁹. That's why we can observe the forces between charges you just rub something on your hair, the comb become charged, and it can attract pieces of paper. So it's a very strong force compared to the gravitational force. This value will be given to you in the formula sheet. You don't have to memorize them. But remember, the form of the Coulomb's law is inversely proportional to the distance between them and directly proportional to the charges. So each charge, so the product of the two charges. The force will be one on the other. It will be equal in magnitude but opposite in direction. If they are like charges, please, if you are staying here, pay attention to my class. Put that down. Come to the front, please. Come to the front, please. Excuse me. Come to the front. I cannot be talking to myself. If you don't like to stay in the class, you can leave. Don't come here just for the attendance. So now we can answer a question based on that simple equation. The electric force is given by this equation. Excuse me, are you in my class? Okay. Two point charges attract each other with an electric force of magnitude. So the force is this. Now he is saying if you triple the value of one of the charges, let's say Q1, we make it 3Q1. So the Q2 is 3 times Q1. And increase the distance between the two charges. So say Q1, Q2, certain distance R1. So Q1 make it 3Q1. And Q2, we don't change it, right? We nothing about the Q2. So Q2 is the same as before. And the distance between them, R2, is changed by how much? By a factor of 3. So R2 is 3R1. Now we want to compare these two forces. Previously, when we have the Q1 and Q2, R is R1, the force is FL, electric, okay, FEL is the force. The new force, FEL dash, let me call it, will be K, instead of Q1 we got 3Q1. And Q2 is the same. R1 is 3 times R1, but the whole thing squared. So now easy to answer the question, right? So what happened, this 3, let me separate it. So there's a 3 from here. 3 into the power 2, 9. So the 9 here. The rest is like the previous, the same thing. So that's how you do this question very quickly and easily. So the new electric force will be 3 over 9 times, that means 1 over 3, right? 3 over 9 means 1 over 3. So the answer is B. Okay. B, right? The new force is 3 over 9 times the new old force. So 1 over 3. No, because the question is, what is the magnitude of the... What is the question? What does the magnetic force between these particles become? What is the new force in terms of the old force, right? I believe this is the right answer. Is the answer given? Yeah. I hope I'm right. Okay. Right. The new force in terms of the old force. Right. Now these things, the table is there not for you to memorize, but to understand, everything, the charges are coming from the basic constituent. Any substance are consisting of atoms, and each atom has electrons and proton. Neutron is also there, but they don't have any charge. So look at it. Both electron and proton has the same magnitude of charge. So we call the basic fundamental unit of charge. You cannot have a fraction of that. Anything has to be in terms of either electron, or as a negative charge will be in terms of how many electrons. Positive charges will be in terms of how many protons. And the mass, of course, they are the elementary particles, so it's very, very small. But still, if you compare these two, proton is much heavier than the electron. Minus 31, minus 27, order of 4, right? 4, yeah. 10 to the power minus 31, minus 27. So that means electron is 1/10,000 times less massive compared to, well, 10. Right. Neutron is the same mass as the proton, but zero charge. You are not supposed to memorize this, but just I'm giving you the table, okay? Quantization, this is important. That's what I was telling you. There's a fundamental unit of charge. If you can make anything charge by rubbing or something, what happens if you take the comb and rub on my hair, I think it will lose some electrons, so the comb become positively charged. It loses the hair. So the hair, on the other hand, will have more electrons, so it will become negative charge. What is moving is not the proton. It is always the exchange of electron. Nucleus is bound to the atom, right? It doesn't move. Only the electron that is moving. So what do you mean by quantized? I mean, any charged particle with Q can have a charge equal to some integral number of the fundamental charge. That's because the charging is because of either losing the electron or gaining the electron. So the amount of charge it gets will be integral multiple of the electronic charge, which is 1.6 into 10 to the power minus 19. So this is called the quantization of charge. That's one important property of charges. Charges are quantized in amount of the fundamental unit of charge. Example question, find the magnitude of the electric force exerted on a point charge by 3E, that is the amount of charge, E mean the fundamental charge, into 1.6 and minus 19, by a point charge minus 5E that is located 7 nanometer away. So it's asking a simple question. We have a charge Q1, which is plus 3E, and we have a charge Q2, which is, where is it? Why am I not seeing it? Third line. Okay. And you're too close to the minus 5. And the distance between them is 7 nanometer. What is the force? You just simply apply the Coulomb's law. It's called the Coulomb's law. So it is done in the board. So just substitute. This, you don't have to know this. The whole thing is K. So for the K, you substitute this. This is the SI unit for that. And Q1, magnitude, I'm only asking for the magnitude. This is the, how did I get this? Actually 3E, right? 3E means 3 multiplied by 1.6 10 to the minus 19. That's why you get 3 multiplied by, this will be 4.8 10 to the minus 19. This is 5 multiplied by 1.6, that become 8. So magnitude only. Divide by the distance is 7 nanometer. Nanometer converted to meters. We have to do that part. So you get this answer. So this is the force between those two tiny particles. And there's a B question. What is B question? Compare this with the gravitational force between the it's a two entirely different question. Compare the electric and gravitational forces between the electron and the neutron in a hydrogen atom. So it has nothing to do with A. It's a fresh question. The charged particles are electron and a proton. Right. So, we apply the Coulomb's law. Electron and a proton, they both have the same charge, which is 1.6. So we can write E squared. Divide by, this is the K. The in the hydrogen atom, right? So the distance between, we can assume the electron is here at the orbital radius, and the proton is here in the classical model. So the radius of the hydrogen atom will be the distance between the electron and the proton. So that's why you put the Bohr radius, that is the radius of the hydrogen atom, and you get this answer. This is the electric force between the electron and the proton in a hydrogen atom. Compare this with what? The gravitational force on any one of them. Gravitation between the electron and the nucleus. Okay, so these two particles are so tiny. Electron and a proton. So M1, M2. Remember the gravitational, Newton's law of gravitation? The force is equal to G, M proton, M electron divided by the Bohr radius squared. So we're going to substitute that. You know the value of G, value of K is very big. The K, this is the whole thing, K is equal to 9 into 8.99 into 10 to the power 9, 10 plus 9. Whereas G, 10 to the minus 11 something. Okay, you put the value of the mass of the electron, mass of the proton, the Bohr radius. This is how small it is, the force. Whereas the force we got for electric force is 10 to the minus 8. The force we got for gravitational force in the minus 47. The huge difference. Order of what? 47 minus 8 is 41. 10 to the power 40. 40 orders of magnitude greater. Right. I will take attendance, then I will continue. Please put your mobile away. I don't want you to be calling in. I will call your names one by one. What's your name? You better stay in the class the whole time if you want to get the attendance. What's your name? Abdullah Al-Barak. Your name? Hussam. And your name? Could you please come here and sit, please, here, both of you. Sorry, Hussam. No, your name? Muhammad Tawil. Muhammad Al-Tawil. Okay. Basil. Basil. B. Where is B? Basil. Okay. Right. Your name? Misbah. Where are you? Misbah. Okay. And your name? Muhammad. I'm sorry, I don't remember the names. Muhammad Yusuf Abdullah. Okay. Right. I already took your name, right? Yeah. All right. Second one? What's your name? Sorry? Sayyid. Sayyid. Sayyid Hamza. Okay. Ayman. Ayman, you better stay in the class the whole time, okay? Right, your name? Muhammad Ali. Muhammad. Where is Muhammad Ali? Al-Azmi? Muhammad Al-Tawil, Muhammad Yusuf. Oh, spelling difference, okay. M-U, Muhammad Ali, yeah, thank you. Right, and yeah. Abdurrahman Al-Harbi. Abdurrahman Al-Harbi. Where are you, Abdurrahman? Ah, here, okay. Am I done with everyone? Could you please, excuse me, come here, sit in the front.
Excuse me. Come in the front. Sit in the front. Yeah, here and here. Come here, please. Here. Here. There's a seat here. What's your name? Khalid. Sit down. Khalid Abdul Musin?
Yes.
Late. What's your name? Ibrahim. Ibrahim. Where are you, Ibrahim? IFGH. I don't see Ibrahim. Up? Yeah, with the E. Okay, I was looking with Ibrahim Mishal. Late. Right. Oh, sorry. Okay. Excuse me. You're late. Please sit in the front, please. Here. There's a seat here. Hey, excuse me, come to this, please. Here. There is a place here. What's your name? Yeah. Please sit here. Please take the bag. Let him sit there. Abdullah. Where are you, Abdullah? Let me put it in alphabetical order.
Between.
Abdullah Al-Qaeda.
No.
Down. Abdullah.
No. Yeah,
Late. And your, excuse me? Please put your phone away. Close your laptop. Phone away. What's your name? Omar Abdullah. I'm wasting my time. Okay. Who else came late? I took your attendance, right? Omar Abdullah. Who else came late? Yeah, no, I didn't. Okay. Muad. Late. Who else? Who came just now? That's it? Okay, what's your name? Sulaiman. Sulaiman. There are two Sulaiman. Sulaiman Rahuddin. Excuse me. Sit here, please. Oh, this is crazy. Right, what's your name? Yaqub. Right. I'm not going to take anybody else's attendance. That's it. The time is 1:20. You know the rules, right? 10 minutes after, you can stay in the class, but you will not be marked as anything. 5 to 10 minutes late. If you come within 5 minutes, you are present. Right? They can come, they can sit, you can listen, but you will be absent. Right, let me continue. So those who came late, don't bother me to take the attendance. If you want, you can leave because I'm not going to take your attendance. It's your choice. If you want, you can stay if you really want to listen to me. But don't come to me asking for attendance. Right, so we come to the direction of electric force. The equation for the electric force is K, the magnitude, Q1, Q2 divided by R squared. Now, how can I assign a direction in a formula? So to do that, we define a unit vector. Let me draw these two charges, Q1 and Q2. So we are talking about the force of charge 1 on charge 2. So this is Q1. The force it exerts on Q2, we don't know whether it is positive or negative. Let me take both of them are positive and positive. So what will be the direction of the force of Q1 and Q2? They are like charges, so they will repel. So the force will be like this, force of 1 on 2. Then we define a unit vector as R12. When you call unit vector, mean the size of the vector is 1. Okay, it is just there for our convenience. We define a vector R12 which has a size of 1 unit length and is directed from charge 1 to charge 2. The direction of R12 is in this direction and its length is 1. So that's why we put this O at the top as a superscript. Now, if I look at this Q1 and Q2 must be substituted with the sign. If both of them are positive or both of them are negative, in both cases it will be positive. Positive multiplied by positive will be positive. Negative multiplied by negative will also be positive. So if they both have the same sign, this will be positive. And the direction will be from 1 to 2. The direction will be from the charge 1 to 2. So we get the force to be in the direction of a vector that goes from charge 1 to charge 2. Yeah. Yeah, I'm looking at the first. Well, let's come to that later. Okay, so let's ignore that. I want to see whether this gives me the correct direction or not. Okay, let me take the example of both are positive. When both are positive, this will be positive. So the direction will be simply the direction of this. That is the line drawn from 1 to 2. Okay. So it works for both are positive. What if both are negative? Same story. When both are negative, what will be the direction of the F12? Will be in the direction that is from 1 to 2. Now let me take the remaining case, which is 1 is positive, 1 is negative. Then what happened? The force on 2 will be towards it. F12 will be towards it. And this is negative. Q1, Q2 is negative. That means the direction will be towards 1, not away from 1. Because this negative sign will flip. It will be the opposite direction to R12. So the direction will be from 2 to 1. So this is perfectly gives not only the magnitude, it also gives the direction in terms of this unit vector. So here is a picture that shows the top one is both same sign, positive, positive. It also apply for negative, negative. Then it will be repulsive force, and the force direction will be in the same direction as R12, and our F21 will be in the same direction as R21. Okay, but when they are of opposite sign, the direction will be towards the charge. Okay, the one that is giving the force. Yeah, yeah. Here, for this guy, yeah. So we didn't written that. So this is the one. This is the two. R12 means the vector that goes from 1 to 2, right? So because they are of opposite sign, the direction will be switched. So the force of this on that will be towards 1, not away from 1. So everything works perfectly nice. Okay, right? Good. Yeah, it was not put there. I don't know why, but no. So we have a question, concept question. The next slide shows 8 possible cases for the horizontal arrangement of 2-point charges. The figure further shows the direction of the electric force vector acting in each case on the point charge represented by large circle. To describe this arrangement with Coulomb's law, the unit vector RO has to be identified. Do all 8 vectors point in the same direction? So I will explain the question again with the picture. So don't worry if you don't get it right away. 2-point charges are shown, 8 possible cases. The figure further shows the direction of the electric force vector acting on each case in the point charge represents a larger circle, right? So this is on the left-hand side, you have 4 cases. On the right-hand side, we have another 4 cases. So we are looking at the force on the big charge, the larger, the big one. Now we are going to check what we learned before. They are, in the first instance, both are positive, right? Both are positive. We are looking at the force on the big circle, not on the small circle. So you know from the nature of the charges, the direction of the force on F will be to the left. And that is the force of the small charge on the big charge. So RO is like this, right? The unit vector is, who is giving the force? The small guy is giving the force on the big guy. So the direction of the unit vector is to the left. Force is also left. Do we agree with what we said? If Q1, Q2 are both of the same sign, the unit vector and the force will be in the same direction. We agree. What about the number 2? This is the RO direction. This is the RO direction from the small to, this is the direction of RO. Here the RO will be this. The direction of RO will be this. Here the direction of RO will be this, because we are looking at the force on the big charge from the small charge. So the guy who is giving the force is the small guy. Right. So look at it. When they are positive, negative, the force is opposite to the unit vector. Here, again, opposite to the unit vector. Here, same direction, because they are both negative. That means the product will be positive. So, and so on. Everything agrees? Any objection? Everything agree, right? Same charge, same direction, F and RO. Opposite charge is opposite direction to RO. Opposite charge, opposite direction to RO. Same charge, same direction as RO. So, electrical phenomena in life science application. We have some model systems to describe application in physics and separately in biology. Our models are stationary point charge, electric dipole, charge parallel plates. I think we saw the electric dipole. No, this is the first time. What do you mean by electric dipole? At the beginning, I told you, when there is a separation of charges, like in the water molecule, hydrogen end, oxygen end. Oxygen end will be slightly negative, hydrogen end will be slightly positive. We call it dipole, okay, electric dipole. When you have two charges separated, one is positive, one is negative, same magnitude, okay, because as much of negative this one, that same amount of positive, the one below, because they are exchanging electron, right? There will be a little bit more electron here, that much of electron will be lost from the hydrogen side. So such an arrangement called electric dipole. So in physics, we have the antenna where we have this charge separation. We don't have to go to the detail. And for stationary point charge, alone solo charges moving, that an example is electron in a conductor metal. And parallel plate, we have an application called capacitors in electric circuit. Maybe you heard resistors, right? Like resistor, another electric circuit element is capacitor. Those capacitors is nothing but two plates. One plate is positively charged, it is connected to the positive side of the battery, and others will become negative charge. In between, gap, okay, no conduction. So such an arrangement is called a capacitor. That's a physics application for that matter. So all our application can categorize into these three models: stationary point charge, electric dipole, charge parallel plate. In biology, we have parallel situation. Point charge, ions in solution, sodium chloride, sodium ion can move, chloride ion can, negative ion can move. Those are similar to the electrons in a metal, isolated charges. Electric dipole is the famous example is water molecule because they are polarized, positive side and the negative side. And this is very important. The cells in our body, they are polarized. Heard about the nerve membrane. Inside is negatively charged, outside is positively charged. So it is like two plates. So if I draw the nerve membrane like this, a cell membrane, any cell membrane is more important in the nerve because of the signal propagation. We have a negatively charged end inside and positively charged outside. So it is like this is one side of the capacitor, this is another side of the capacitor. So it's like the parallel plate capacitor in physics. So the nerve membrane can be modeled as a capacitor, charged parallel plates. So we will look at the first model. One example is lattice ion in a metal. The ion is electron here. The electrons moving freely between the in a nucleus atoms that are fixed in place. So while they move, they can scatter, hit, collide, and change its direction like this. Dipole. So what is a dipole? I already told you, but let me again define it properly. Configuration of 2 point charges of equal magnitude and opposite sign separated by a fixed distance is called electric dipole. So we can have one charge here, positive, and another charge of the same magnitude but negative, and separated by a distance d between them. Such an arrangement is called electric dipole. And we have some terminology here. This will have what is called the electric dipole moment. The symbol is mu. It is defined as the charge of one of these dipoles, q, multiplied by the distance between them. So it is called the dipole, electric dipole moment of this molecule. Suppose a molecule. So example is water molecule. So the hydrogen end of the water molecule is positive and the oxygen end of the water molecule is negative. Water molecule being such a polar molecule has lots of significance in life. Why this happen? Because hydrogen atoms they join with this covalent bond. That means they share the electrons, right? You know that part, I hope. They share the electron. So one electron from this, one electron from this, then they make this covalent bond. But however, it is going to be a little bit ionic because oxygen being very electronegative, it will keep the electron closer to itself than to the hydrogen. So the oxygen side will be slightly negative and the hydrogen end will be slightly positive. That's how they form this dipolar molecule. Right. So this is the electric dipole by definition. The polar nature of water molecule allows them to bond to each other in groups, and it's associated with surface tension of water. Probably this you learned this in your chemistry. I don't know how much you learn. Because they have this one end positive, one end negative, they can group together because the oxygen end of one oxygen end of one water molecule can join with the hydrogen end of another water molecule because this is negative, this is positive. This is also called another name, hydrogen bond. Okay, hydrogen bond. So that will make them to have a high surface tension. What do you mean by surface tension? Intermolecular force is greater, so they stick together, they form a spherical shape and so on. So that is one reason for their high surface tension. And it has a lot of application or a lot of implication there. it causes water vapor at sufficient vapor pressure to depart from the ideal gas law, because you cannot ignore the molecular interaction, because what is ideal gas law? We say we ignore the molecular, say no molecular interaction. But here we have a molecular interaction because of this polar nature, so it will depart from the ideal gas law, they become condensed quickly. So this can lead to condensation and phenomena like cloud formation, fog, dew point, etc. Another one is this dissolving. Water is a very good solvent, right? Water is, it can dissolve, they can clean. That's because, for example, if you put sodium chloride, that is salt, into water, how they get dissolved? Because this guy will, the hydrogen end of the water molecule, which is positive, will gather around the chloride ion, and negative side of the water molecule, oxygen, will gather around the positive sodium ion, then they will be separated. That means they get dissolved in water. It also has great deal to do with function of water as a solvent of life in biological system. Let me tell the phenomena. In countries which get very cold, winter countries, like in the north, the water in a lake or the ocean freeze. But below the ice layer, there is water, liquid water. That's because of water being a polar molecule. It has a certain property. If you take any liquid, say alcohol, for example, I hope it is so with alcohol, any liquid, any other liquid other than water, when you cool the temperature, what will happen to its density? What do you expect? When you increase the temperature, it will expand, right? So density will become less. So decrease the temperature, it should shrink. The density will become more dense. Okay, they come closer, more dense. But for water, it's not exactly like that. It happens up to 4 degrees. You see, bring from the room temperature, bring to 4 degrees, up to 4 degrees, it will shrink. Density will become more dense. After 4 degrees, because of this hydrogen bonding, water has hydrogen bonding, not ice. As you cool it and it become less hot, as it comes to form the solid formation, come closer and closer, it loses this hydrogen bonding, then they expand. So after 4 degrees, the opposite happens. Its density will increase. So 4 degrees is the critical temperature. So when you are in a in the winter the temperature gets cold, yes, you will see the water become colder and colder. So the cold water is denser, it will go down, so there will be a convection. So everything will become 4 degrees quickly. But after 4 degrees, let's say it become 3.9 degrees. 3.9 degrees water is less dense than 4 degrees water. So it will stay in the top, it will not go down. So the top layer will be freezing, but below it will be liquid water. There is no convection now. There is nothing going down and replaced by something coming up. There nothing like that happen. So the top layer will be freezing by conduction. There will be no convection. So this can, in this manner, the fish and marine life can live in the liquid water, survive in the 4 degrees temperature. Yeah. Yeah, no, after 4 degrees, up to 4 degrees, this will happen. Denser water will go down and it will be replaced by the less dense water coming. So in convection, everything will be 4 degrees. Ice is less density than liquid water. That's why ice floats. But that is not what you expect to happen, right? When something is solid, it should be denser than, but it is anomalous. We say it's not normal. Okay? Because only for water. I don't know any other substance. I believe water is. I cannot tell with certainty. You can look it up. But water is that is why we call it solvent of life. So it allows the fish in the winter countries to survive, because below the ice it is still 4 degrees water. Okay. So we were talking about some systems, models in life sciences and physics. So we started with the dipole. So in life sciences, this water molecule is an example. So then this third model is parallel plate arrangement. So in physics, what we have is a capacitor. It's like two conducting plate, but a gap in between, nothing. I mean, gap can be an insulator which doesn't conduct electricity, but the plates are conductors. So when you connect it to the battery, say positive side will make this one plate positive, the other one negative. So this is called capacitor. It's a very important, very commonly found element, circuit element in electronics. But we have in our body also. Our cells have the membrane of the cell, capacitors, that's the membrane. So the two tissues of a cell membrane. So one is in a normal state positively charged outside, and this membrane is negative charged, right? Intracellular. Out of the cell, it is positively charged. So this cell membrane, the two tissues of the membrane is like capacitor plate, parallel plate capacitor. They are parallel to each other. But it's circular one, like a sphere, but there it is just flat plates. In the case of parallel plates with equal but opposite charges, a simple form of the electric field is formed. In a capacitor plate, we actually have an electric field, very simple. It directed from positive to negative. And that electric field is a constant uniform electric field. The parallel plate model describes all biological membrane system, where charges are separated into the opposite phases at a fixed distance between, determined by the lipid bilayer thickness. So this is actually formed by some phospholipid bilayer, something, right? Yeah. So it's like we have this, and from this the upside down. So this will be one layer outside and the other layer inside the cell. So this membrane of the cell makes the positive plate and the negative plate of the capacitor. You can treat it like a capacitor. They are semi-permeable. You know what it means. Permeable mean allow transport, right? Semi mean it's not completely. So semi, half. Membranes allow ions to pass selectively. I think big molecules may not pass, which establishes a major application of the interaction of mobile point charge with a charged parallel plate system. So the ions can pass through this membrane, semi-permeable, and even they have gates which opens and close and allow only certain ions to pass. So in the next slide, we show such a membrane with stationary charge cations.
on the internal, the extracellular side, and anions in the internal side. And also some example of a potassium cation that transported across the membrane. So here it is. So this is the membrane, right? And this is the other. This is inside the cell. This is outside the cell. So it could be, forming a sphere. So these are what we call some protein molecule, right? But it has the name phospholipid bilayer. So these are lipid molecules, something. So these are the membrane. This is one plate. The inner one is the other plate. And in a resting potential, you have the inside the cell negative. Please correct me if I'm wrong. Yeah, correct. And outside will be?
The outside will be positive.